But we say a graph is a tree if it's simple, connected, and contains no cycles. So simple means I don't have any self loops from one node to itself. I don't have any multiple or parallel edges, just single edges. Simple also implies that it's not directed. This is an undirected graph. And connected means that there's at least one path between any two vertices or nodes you pick. If I use the word vertex, it means the same thing as node. If I use the word node, it means the same thing as vertex. Those are synonymous. So it needs to be simple, it needs to be connected, it needs to contain no cycles. So this is a tree. It's a tree. What? Sorry. It's a tree because it's simple, it's connected, and it contains no cycles. If I were to add even one more edge to this graph, boom, I would get a cycle, and this is no longer a tree. And if I were to delete any edge from this graph, well, now it's not connected, and it's no longer a tree. So trees live right on the border. You know, they're like right in between that definition of like, it's the minimal connected graph, but also the maximal acyclic graph. You can't add any edges without getting a cycle. You can't delete any edges without being disconnected. That's what makes a graph a tree. And maybe next time I'll spend a little bit more time talking about trees. I say next time, I mean 2 years from now. A graph with n vertices is a tree if and only if it satisfies any of the following descriptions. The standard description I just gave you is it's a connected graph with no cycles. Another way you could define a tree is you could say a graph is a tree if for any two vertices in the graph, there is exactly one simple path connecting them. The reason this is equivalent to the first definition is because if you had two paths connecting two different vertices, well then you could traverse one of those paths in the forward direction and then the other path in the reverse direction, and then you've just created a cycle. But a tree can't have a cycle. So it's connected and acyclic. The third description, another way you could define a tree, is you could say a graph is a tree if and only if the graph is connected and has exactly n minus 1 edges, where n is the number of vertices. The reason for that being is imagine a graph with one vertex or one node, right? That's a tree. It's connected. It doesn't have any cycles. If I add another vertex, I also have to add an edge connecting those. So I add one vertex, I add one node. And every single time I add an additional vertex, I have to connect it to the existing graph structure with one edge. I can't ever add two edges to connect my new vertex, or that would form a cycle, but I do have to connect it with one edge so that it remains connected. And that means I'm always going to be in a situation where I've got one fewer edge than vertex. A fourth way you could describe or define, a fourth way you could define a tree is you could say that a graph is a tree if it's connected, but if any single edge is removed, it becomes disconnected. And a fifth way you could define a tree is you say, a graph is a tree if and only if it has no cycles, but if any new edge is added between existing vertices, a cycle is created. And so I've typed this out. I'll probably upload this lecture notes to the website later. But I've typed out, in words, if you're interested in reading this, the reason why these definitions are equivalent to one another. But it's not terribly important. The way I just defined tree, I said that trees were simple graphs, so that means a simple graph is not directed. But I could say the words directed tree, and so that means, imagine a graph that's just like a tree, but I can assign directions to their edges. Now I have a directed tree. If I had a directed graph, I could not only just count the degree of each vertex, but I could count both the in degree and the out degree. So let me draw you a little directed graph really quick. If I were looking just at this vertex, it would have in degree 1 and out degree 1. And this vertex would have in degree 2 and out degree 0. For a simple graph, the degree is just the number of connected edges to a vertex. But for a directed graph, you can count separate in degrees and out degrees. A hierarchical tree is a directed tree where one specific vertex is designated to be the root. The root is special in that it has an in degree of 0, and every other vertex has an in degree of 1. So let me draw you a hierarchical tree. Okay, so the root is the one node that has an in degree of 0, and notice all of the other nodes have an in degree of 1. That makes it a hierarchical tree. A good example of a hierarchical tree is the storage directory of folders on a PC. So every folder on your computer belongs to only one parent folder, except for the root of your storage system, which doesn't belong to any parent folder. In a hierarchical tree, pairs of adjacent vertices are labeled as parent and child. So if I'm talking about this vertex as being the parent, then it has 3 children. That one's a child. The hierarchical tree might have a situation like this going on where I would say that this vertex right here is a descendant of this vertex here, which would be its ancestor. So it's not directly the parent, but the descendant is in the directed path from the ancestor. There's a directed path that exists from the ancestor to the descendant. So it's a little bit more generic or general definition versus just parent and child that have to be adjacent to one another. A binary tree is a hierarchical tree where the out degree of every vertex is either 2 or 0. So I didn't draw a binary tree in green. A binary tree is one where the out degree is either 2 or 0. So a binary tree can only split 2 ways when I go from the root, and then each parent can only have 2 children in a binary tree. Right? That's what a binary tree looks like. A good example of a binary tree is the structure of mathematical expressions. So I could ask you, draw the binary tree corresponding to this expression. And it looks like the last thing we would do in evaluating this expression is maybe divide. And what is it that I'm dividing? Well, in the numerator, I'm going to be multiplying some things. In the denominator, I'm going to be subtracting some things. What am I multiplying? Well, I'm multiplying one factor that's going to be the sum of two things, and another factor that's going to be an exponent. What am I subtracting? Well, down in the denominator, I'm subtracting 4 minus 2. In the numerator, I'm adding 1 plus 2, and then I'm doing the exponent to 3 raised to the power 5. So this is kind of like a binary tree corresponding to this expression. And the way I would evaluate this expression is I would start at the lowest levels, right, and combine the 1 plus 2 and the 3 to the power 5. And then I would have to multiply what do I get from here times what do I get from here. And I'd subtract 4 minus 2. And then lastly, I would divide what I get from these nodes. So a binary tree could be used to sort of organize how you're going to evaluate an expression. There are 3 methods for visiting every node in a hierarchical tree exactly once. So these are called methods of tree traversal. The 3 methods are pre-order, post-order, and in-order traversal of the tree. If you want a pre-order traversal, you'd go parent and then left to right. Post-order goes left to right and then parent, and in-order. In-order is special because it only works with binary trees. You wouldn't do an in-order traversal of any other hierarchical tree, but you would just do an order for binary trees. So here's an example of pre-order traversal. What if I am trying to plan a book? I'm going to write a book for what audience? Trying to decide who should I write a book for. Maybe I'm going to write a cookbook. And in my table of contents of my cookbook, I'm going to have 3 main sections. My 3 main sections are going to be salads, entrees, and desserts. And within the salad section, I don't know, are there different types of salad?
Pasta salad.
Pasta salad? Potato salads? Leafy salads? In the entrees section, maybe I'll list different ways of preparing beef and chicken and fish. Those can be subheaders. And in the desserts section, we'll have pies and cakes and
Ice cream.
puddings. Sorry, I'd already written a P.
Puddings over ice cream is pretty easy.
Okay, so if I want to create a table of contents for the second or first page of my book, right? Creating a table of contents would be an example of pre-order traversal, because I'm going to start by writing the name of my book, and then I'm going to write the name of the first header, and then I'm going to start writing the names of all the subheaders. And so as I'm traversing this tree, I traverse the tree like this. Think about going around, is that clockwise? No, that's counterclockwise. Think about moving around your tree and a counterclockwise direction. That's how you get pre-order traversals. You move around the whole tree in a counterclockwise direction. And as you move past a node or a vertex, you're going to pick it up and you write it down. So the total table of contents is going to say cookbook, and then salads, and then pasta, potato, leafy. I should not write a cookbook. So that's one way you can remember pre-order. Pre-order is it's a counterclockwise way to draw a loop around your whole graph. It's also how you write a table of contents. And when would this matter in computer science? I don't know. I'm not a computer scientist. But if I were creating a directory in computer storage, I would think I have to create the folder before I create contents of the folder, right? And so that's kind of the same order in which you, I don't know, would naturally put that together. All right, post-order traversal is kind of the opposite. We're going to do left to right first and then get to the parent. Instead of doing parent left right, we do left right parent. That's post-order. So what if I have a tree like this? This would be useful if I'm deleting a tree. Because if I'm going to capture this node and then this node and then this node and then go up to the parent, you've got to delete the contents of your folder before you delete the folder itself, right? You clear out the contents and then you move up and delete it. And then you clear out the contents of the next one and then you move up and delete it. And then you can delete the overall structure. It says, or when evaluating math expressions. I guess that makes sense if you've got like a big sum, you've got a sum of multiple terms, or if you've got a product of multiple factors. In order traversal, like I said, this is the third type and the last type of tree traversal. It applies to only binary trees, and it would proceed left parent right. So let me draw a quick binary tree, and then I'll show you how to label this. I would do this node first, this node, and then this node, because it goes left parent right. And I did the left side of this, so then I'll do the parent, and then I'll move on to the right side, in which case I do left parent right, like so. So the traversal goes 1, 2, 3, 4, 5, 6, 7, in that order. And to be honest with you, I didn't think of any applications off the top of my head for why in-order traversal would matter. Doesn't mean I don't. It doesn't mean it doesn't matter, but
This is used in computer science a lot.
good. All right. Traversing graphs can have one of two objectives. Finding a vertex with some particular property, and this could be solving a maze, right? Like in a maze, let me draw a little maze. In a maze, they're typically drawn so that there's sort of a grid underlying the maze. I don't know if you guys do a lot of mazes. I'm sure it used to be a much more common form of entertainment back before people had, Nintendo Switch and Xbox and stuff. But maybe if you were a child of like the 1950s and you only had the mazes in the back of the newspaper, you know, this is going to be the vertex or the node where you start, and then there's going to be some objective or some goal of your maze, like you want to reach the finish. And the problem with mazes is that you can't go directly from start to finish, but there's some kind of wall structure that would prevent you from getting there directly. So maybe it looks like this. And you think to yourself, I want to get from start to finish in this maze. And so that's what I mean by finding a vertex with some particular property. In this case, the vertex that has a particular property is the finish vertex, but I'm only here at the start vertex. So how do I come up with an algorithm that can traverse my graph? And that maze might not look like a graph, but it's kind of a graph if every little square is a vertex. Then you could draw a corresponding graph to this maze. Right? So mazes are graphs. And so that's an example of the first type. The other thing is, what if I want to visit every vertex once? Maybe I'm trying to index something, create an index list. Maybe I just want to do something to change or modify every vertex in my graph. So those are my two goals for traversing a graph. The following algorithms assume we don't know where the vertex is. In other words, the following two algorithms are searches or ways to move about a graph where I don't know where the finish line is. I don't know where the special vertex I want to get to is. We're assuming we don't know what that is. So how do we find the finish if we don't know? We just know where to start. And we also assume that all edges cost the same amount to traverse. It costs like one operation to get there. Two types of ways we can do this: a breadth-first search or a depth-first search. So breadth first means we explore all neighboring vertices before moving to vertices at the next depth level. So if this is my start point and this is my finish point, and imagine this graph is connected. Breadth first means I would try this one, and this one. And that would be one depth level because those are all immediately adjacent to the start node. The next depth level would say, okay, now I'm going to find nodes that are adjacent to nodes that are adjacent to my start. So in other words, I would try this one, this one, this one, and this one. And then I would say, okay, let me find nodes that are adjacent to nodes that are adjacent to nodes that are adjacent to my start. That would be the third depth level, 1, 2, 3. I would get this one, and then at the fourth depth level, I would get to my finish line. So one question I could see myself asking on a quiz or a test coming up is like, here's a graph, and I could ask you to label in order the nodes and how they would be traversed in a breadth-first search. In a depth-first search, you would go as far as possible before backtracking. And so the way this might look for depth first is you might say, I'm going to go in this direction and count 1, 2, 3. Oops, I didn't find anything. Go back in this direction, 4, 5. Oops, didn't find anything. Go back. And then try 6, 7. Oops, didn't find anything. And then go this way, 8, 9, 10. So then I could ask you a question that says, in a depth first search, number off the nodes in the way they would be traversed. Okay, so breadth first and depth search are words that you use whenever the edges of your graph don't have any weights assigned to them. But there are some problems where we want to assign weights to the edges in a graph, and this is what we would call a weighted graph. And an example of a weighted graph, that might be like this. If I had a graph that says Kansas City, Tulsa, Denver,
St. Louis.
Miami,
Ah, yes, north of Tulsa.
maybe, yeah. Well, they're isomorphic, they're graphs. The position doesn't matter. It's just a graph. The weights of this graph might be something like 1, 3, 20 or something like that. Because I want to communicate something about the cost of traversing an edge. That might be the distance, physically distance. That might be the amount of gasoline your car has to burn. That might be the amount of time it takes to travel there. It might be the cost of a plane ticket to go from one place to another. But your weights on your edges, typically in this kind of problem, represent some kind of cost, either time or effort or distance or money to traverse an edge. So we might want to find the shortest path from one vertex to another in a weighted graph. Or if you want to connect the entire graph and make sure that there's at least one path between any two vertices, what's the least costly way that you can connect a graph? Here's another example. What if I have a whole bunch of cities, right? Like here's Seattle, and here's LA, and here's Denver, and here's KC, and here's Chicago, and here's New York, and here's Miami, and here's, Dallas or whatever. If I say I want this to be a connected graph, but I want to do it in the cheapest way possible, now your job is to decide, how am I going to connect this up? If I want it to be connected, I don't need any cycles, so I don't need connections between Seattle and LA and Denver, right? Like I don't need it to be a triangle here. I've got to choose, do I want Denver to connect to both of these? Or maybe I don't want Denver to connect to both of these. Maybe I want Seattle to connect to both of these. It doesn't really matter. I just need my graph to be fully connected using the least cost possible. And so you've got to choose how to do this. And the edges could potentially cost more or less. But that's the idea. Maybe the only thing I care about is that these cities are connected by an interstate system, so that we can move goods and even military equipment quickly and easily. Or maybe my only goal is that I need these to be all connected into an electrical grid. And so I don't necessarily need an electric connection between Denver and Dallas that can have like a massive high current, high voltage, transmission lines between Denver and Dallas directly. As long as Denver is connected to Kansas City and Kansas City is connected to Dallas, they'll still be on the same grid. And so if I have to put down fewer miles of transmission lines, that saves on cost. And maybe that's all you want, is you want the least cost electric grid, but down the least amount of transmissions. Another way you could do this, since you're all computer scientists, is you could say, what if these are servers in a distributed internet, right? I need the internet to be connected so that I can talk to my cousins in Iran or whatever. But just kidding. Iran shut down their internet. But we could make it so that maybe my connection from my PC at home goes through Dallas and it goes through Warsaw, Poland, and then it goes to Tehran, or maybe it goes directly from Dallas to Tehran, but it probably has a lot of intermediate steps. Because the only goal is connectivity. You don't need everything to be fully connected, but we want to do it in the cheapest way possible. So that's another type of problem. Such a thing is called a spanning tree. If I create a spanning tree, by starting off, I could assume any kind of graph shape, and I just remove edges until we have a tree. That's a tree that spans the original graph. And a minimal spanning tree is the spanning tree with the least total cost. There's two ways that you could create a minimal spanning tree. There is what I would think of immediately as a procedure for creating the minimal spanning tree. It's called the reverse delete algorithm. It says we start with a graph. Start with any graph and assume that it has some cycles. Assume it's not already a tree. And then find the edge in this graph that has the greatest weight or the greatest cost associated with it. And then we think to ourselves, can I remove this edge, or is this edge going to disconnect the graph? Well, if it's about to disconnect the graph, I can't remove it. And so we stop and we consider a different edge with the next greatest weight. But if I am allowed to remove that edge, and my graph won't be disconnected, then I'll go ahead and remove it. And by doing that, it's like being as greedy as possible. I'm saying, let me remove the heaviest or the most costly edge every single time that I can, and you keep removing edges until you can't anymore. That's a way to create a minimal spanning tree. Another way of doing this is called, I don't know how to say that, Kruskal's? Kruskal's? Don't know how to say that. Kruskal's algorithm. Okay, I hate mispronouncing things, but I know I'm mispronouncing it. It's another procedure that's gonna work, but it's a little bit harder to understand. You're gonna start a new graph that's gonna have exactly the same nodes or exactly the same vertices as your original graph, but it starts with no edges, just a bunch of disconnected vertices. And then we find edges in the original graph that have the least weight. And we will add the edge from the original graph with the least weight to it, or the least cost, unless it would create a cycle. And if it is going to create a cycle, we do not add it. And we continue to add edges with the least weight until we cannot add any more edges without creating a cycle. So the reverse delete algorithm is relying on that kind of idea that a tree is the minimal connected graph. And Kruskal's algorithm is relying on the idea that a tree is the maximal acyclic graph. But the interesting thing is, regardless of which algorithm you use, you will always get the same minimal spanning tree. Now, it turns out that in practice, this algorithm is much faster, much more efficient as an algorithm for large graphs, right? For small graphs, it doesn't even matter. But if you have a really large graph, like a social network or whatever, then you want to be as efficient as possible with your algorithms, in which case you would never use the reverse delete algorithm, you would always use this one. So I gotta assign some edge weights here. Gotta make something up. The way that the Kruskal's algorithm would go is I say I'm going to create a new graph, G prime, that has exactly the same nodes but no edges. I start with all the vertices, no edges. And then I find the one with the least weight. It would be this one at the bottom. I can add this without creating a cycle. Perfect. And then I'll find the next one with the least weight, the number 2. I could also add that without creating a cycle. The next weight with the number 3, I could add that without creating a cycle. The next one with the number 4, I could add that without creating a cycle. The next one with the number 5, I could add that without creating a cycle. But the next one is the number 6. I can't add it because it would create a cycle. Then the next one's number 7. I can add that without creating a cycle. The next one's number 8, but I can't add it or I would make a cycle. So this is my minimal spanning tree. That makes sense? Notice I would get the same thing if I just went back and I deleted the heaviest edges, right? Like if I started with deleting edge number 8, and then I think, can I delete number 7? No, I couldn't delete number 7 because it would disconnect my graph. Can I delete number 6? Yes. And then I would think, can I delete number 5? No. Can I delete number 4? No. Can I delete number 3? No. Can I delete number 2 or number 1? No. So you get the same, but it turns out in terms of computer execution, Kruskal's is faster. The next one is called, how do you say that? Dijkstra's algorithm. It's a procedure for finding the shortest path through a graph from a starting vertex to a final vertex, kind of like solving the maze problem. And once again, the location of the final vertex is unknown. And so you're like, this sounds familiar. This sounds like the breadth first search or the depth first search that we talked about earlier. The difference between Dijkstra's algorithm and a breadth first search is that we're not just going to use depth layers, but we're actually going to have a weighted graph, and the cost so far is going to behave like our depth layer. In other words, we're going to prioritize exploring vertices that have the lowest cost to reach. So it's going to kind of be like we have a starting vertex and we're going to expand away from the starting vertex, but we're also going to take into account the weight of the edges. So that's the procedure. First, we explore the starting vertex by calculating the cost to reach all adjacent vertices. And of course, the cost to reach the adjacent vertices are just the weights of the edges. I actually had the time to make an example for this one. So if this is my starting vertex in green, the next vertex that I'm going to explore is going to be this one, because do you see the weight is only 1 along this edge? And so the next vertex, the first vertex I'm going to take a look at is this one in blue. And then when I get to this blue vertex, the way that we explore it is we say the cost to reach it is 1. And what about the cost to reach its neighbors, the vertices that are adjacent to this one? Well, it would actually have a cost of 2 to reach this vertex. If I started from start, it would be 1, 2. What is the cost to reach this vertex? 3. And like I said, when we explored the start vertex, we found out that the cost to reach this one was 2 and the cost to reach this one was 3. Okay, now among all of these blue vertices, which one has the lowest cost to reach? And we're not including this one anymore because it's already been explored fully. But okay, the blue vertices, which one has the lowest cost? 2, 2, 3, 3. I guess I better pick one of the 2s. So let's explore this vertex right here. And exploring this vertex means I look down at its adjacent vertex and I give it a cost to reach. And so it costs me 3 to reach this vertex. And now we can say we've explored that one. In my next step, I look at the blue vertices and I say, that one with the number 2 has the smallest cost to reach it. And so I'm going to explore this blue vertex by determining how much does it cost to reach this vertex. It's kind of a tricky question, because if I reach it this way, it would only cost me 4. If I reach it this way, it would actually cost me 6. So it depends on the way your computer is implementing this algorithm, right? Whether or not this computer program is checking for other adjacent nodes that we've already reached, in which case you might detect the number 4, or whether or not you're just adding the weight of this edge to the previous cost so far. And so your computer is either going to label this vertex as a 6 or a 4, depending on how your program is written. Then we still have to finish exploring this vertex that has the number 2 cost to reach. It says over here, this vertex has what cost to reach it? 5. And then down this way, this vertex has what cost to reach it? 3. And then this vertex is also adjacent to that 2 vertex. So this vertex right here has a cost of, yeah. It depends on, again, how your program's written. Is it written in such a way that it just takes the 4 and adds it to the 2 and gives you a 6? Or is it going to be written in such a way that it looks for other adjacent explored vertices like this 3 and potentially adds a 2 and to make it a 5? That's kind of a very granular question, very specific question that I don't know if we need to explore in this class. Okay, now I have fully explored the 2 vertex right here, so I'm going to put a little red line through it. And I noticed there's some other vertices that we've already fully mapped out and explored, like that one and that one. Even this one over here. Technically, we counted this, not right now, but whenever we did the starting node. When you explore the starting node, you roll that one out. Next, I would have to check out this vertex, the one that has a cost of 3 to reach it. And exploring this vertex means I figure out what's the cost of this one. Down here in the bottom left. 9. And what's the cost of this one over here? 6. And so now we can say we've explored that one, and for that matter, we've explored these guys because we've got their full connectivity. The next thing I would do is I would say, well, this one over here, it has a cost of 5. So let's explore this guy, and it would say this vertex has a cost of 7. So finally, we found the shortest path to this finish line, and it had a cost of 7. That is a demonstration of Dijkstra's algorithm. And because Dijkstra's algorithm does not know the location of the final vertex, it starts at your start vertex and it branches out in all directions. You're branching out in all directions, trying to find the cheapest path from one node to the next in Dijkstra's. Okay, more definitions. A Euclidean graph is a new type of graph. A Euclidean graph is a simple planar graph where the locations of the vertices are significant because the edge weights are calculated as the Euclidean distance in the xy plane. Euclidean graphs are in contrast with what we previously used as the definition for graph, because when I originally introduced graphs, I said like the locations of the nodes don't matter. You can move them around and they're like the same, it's just the connectivity that matters. But in a Euclidean graph, it's not just how the nodes are connected, but also where they are is important, if we call it a Euclidean graph. This makes these Euclidean graphs a good representation for transportation systems, whether it's water, or electricity, or people, whatever you're transporting. You care about the distances in between locations. So the A-star algorithm is a procedure for finding the shortest path from a starting vertex to a final vertex in a Euclidean graph where we know the location of the final vertex. The A-star algorithm is like Dijkstra's algorithm, but you know the location of your final vertex. If I want to go from here to Wendy's, I know the GPS coordinates of Wendy's. I know where my final vertex is going to be. So that's the benefit, is that A-star is not just going to search in every direction. I'm not going to try out driving to intersections that are in the opposite direction of the Wendy's, because I at least have an idea of where I'm headed. And that's why A-star is going to be a lot faster than Dijkstra's. And this is an extremely applicable problem, because like Google Maps, right? Like that's what Google Maps does, is you pull out this app on your phone, you tell it a place, which is, the Earth is a sphere. It's not a perfectly flat Euclidean plane, but we can assume on small distances that it's a flat plane. And what Google Maps is mostly trying to do is find the shortest path through vertices, which are intersections of streets, along edges, which are the streets themselves, to get me to my destination vertex. Now, Google Maps is clearly a little bit more sophisticated because it's got to take into account like traffic and whether or not you're going to hit an intersection and what the speed limits are along these roads. So Google Maps is fancier, but the base, the core logic is the same. The difference then between Dijkstra's algorithm and the A-star algorithm is that not only are we going to consider the minimum cost so far when we explore a vertex, but we're going to take the minimum of cost so far plus heuristic. When I consider which vertex to explore next, I have to consider the minimum of the vertices cost to reach plus heuristic. Heuristic is a fancy word that means the distance as the crow flies. From that vertex you're considering to your final destination. From the intersection you're considering driving to next to the Arby's or the Taco Bell. Whatever your poison of choice is. So let's talk about this. What if this is my starting vertex and this is my final vertex I'm trying to reach? What would the A-star algorithm do? Well, the first thing I'm going to do is I'm going to take this starting vertex and explore it. And exploring it means I'm going to look at these two adjacent vertices and I'm going to calculate their cost to reach plus heuristic. I'm going to label this vertex 0 and this one 1 and 2. So for vertex number 1, the cost to reach is looking like the square root of 1 squared plus 3 squared, which is the square root of 10. the heuristic is going to be square root of 7 squared plus 5 squared. 7 squared is 49, 5 squared is 25, so we're talking about square root of 74. So in total, the cost to reach plus heuristic would be square root of 10 plus square root of 74. 11.76. What about 2? My second vertex. The cost to reach would be the square root of 2 squared plus 2 squared, the square root of 8. The heuristic is the distance from my second vertex to the final vertex, which is going to be the square root of 6 squared plus 6 squared, the square root of 72. And the square root of 8 plus the square root of 72 is 11.31. So whenever I am the A-star algorithm and I'm trying to decide what vertex do I explore next, I'm going to explore vertex 2 next because it has a slightly lower cost to reach plus heuristic. So as I explore vertex number 2, I'm going to have to reach out to this vertex, we'll call it 3, and this vertex called 4, and this vertex called 5. And for number 3, reaching the vertex number 3 is going to be the cost of reaching vertex number 2, which is square root of 8, plus 3, right? Because I'm going to go from vertex 0 to 2 to 3. Then on top of that, I have to add the heuristic, which is going to be the square root of 6 squared plus 3 squared. So the square root of 36 plus 9 is 45. So here we go. Square root of 8 plus 3 is my cost to reach, plus square root of 45 is my heuristic. And we get 12.54. What about number 4? My cost to reach is going to be square root of 8 plus square root of 8, because I'm going to go from vertex 0 to 2 to 4. And my heuristic is going to be the square root of 4 squared plus 4 squared, which is 16 plus 16, which is 32. It's also 11.31. And then number 5. Got to figure out the cost to reach number 5. Plus the heuristic is going to be 2 squared and 6 squared, so that's square root of 40. That's 13.15. Okay, so now I think, do I want to explore vertex 1, 3, 4, or 5 next? I'm considering the total cost to reach plus heuristic for 1, 3, 4, and 5. And I think 4 actually has the lowest cost to reach plus heuristic. The problem is there's nothing to explore, right? That's not connected to any other vertices. And so that gets ruled out, I guess. And I think, do I do 1, 3, or 5 next? And 1 has the lowest cost to reach plus heuristic. And so the only thing I haven't explored from number 1 is this. We'll call it vertex 6. And then I calculate the cost to reach vertex 6, which is going to be the cost to reach vertex 1 plus 4, and then the heuristic, which is going to be the square root of 1 plus 7 squared. So it's going to be the square root of 50. Let's try that. $14.23. Okay. So now I think, what do I have left? 6, 3, and 5. 6, 3, and 5. It looks like 3 has the lowest cost to reach plus heuristic. And so let's explore number 3. And the only thing I haven't explored from number 3 is this node. We'll call it 7. And 7 is going to have a cost to reach. That's the same as number 3, square root of 8 plus 3, plus the square root of 10. That's how I get to number 7. And then the heuristic from number 7 is 5. So I get 13.99. To get to, actually that's the total distance from the start to the finish if I go through 1, 3, 7, finish. The question is that actually lower than the heuristic of 5, which is my only other option now? No, it's not. So 5 actually might be a faster path. And so before the algorithm ends, I've got to explore number 5. And I could reach out to this node number 8 and node number 9. Maybe your algorithm is smart enough to realize that even if we figure this out to number 9, it's going to be a dead end. But then let's figure out number 8 next, right? It's the last thing. Let's figure out which path is really the best. To get to number 8, you would have to do the distance to get to number 5, which is square root of 8 plus 4, plus an additional 4 to get to number 8. And then the heuristic from number 8 to the finish line is going to be the square root of 8. So I've got 8 plus 2 times square root of 8, 13.65. That is faster than from number 7. So it turns out the fastest route is this. You go to the start, you begin at the start, and then you go to 2, 5, 8, finish. And the A-star algorithm follows that procedure for deciding which vertices to explore next. It seems a little bit trivial when you have a graph that's this small, right? Like you as a human can quickly look at and decide which paths you're really going to try and which ones you don't need to try. But for a computer, it's not trivial, right? Computers don't inherently know how to do pattern recognition, so you've got to decide some kind of procedure. And A-star algorithm is nice because it will always find a path if one exists, and I think it always finds the optimal path too. And in many cases, you don't even have to explore every single path. It just happened that way because our graph was relatively small.